Okay, and we're starting. So I had a few examples on the board last time. Let's get through those, and then we'll move on to bigger, better things. So I did one for you, and so we want to prove A related, B. Limit as x approaches 3 over 2, 4x squared minus 9 over 2x minus 3 equals 6. And the limit as x approaches 2 of x squared equals 4. Okay. We want to prove these things. So let's move on to B. So how do we start this process? First thing you write down. Yeah.
Epsilon is greater than 0.
Let epsilon greater than 0 be given. It's always the first line. Then?
You can let, I forgot the snake.
Delta?
Delta,
Yeah.
we have to put a number to it, right?
Yeah, so what do you write?
Suppose delta is equal to.
Well, choose is a better word,
Yeah.
right? Choose delta equal to, now we're going to figure that out. Then, if we want to show that x is approaching A, if our x is close to 3 over 2, within that distance delta that I just told you, then we have our f of x minus the L. Ultimately, I want to be able to say that it's less than epsilon. So I'm going to fill in a whole bunch of stuff here with the goal of ending and saying less than epsilon. Now, as scratch work, how do I figure out what should I choose to have? Yeah? So we're going to go over here, one absolute value of 4x squared minus 9 over 2x minus 3 minus 6. You can factor 4x squared minus 9, difference of squares. It's 2x minus 3 times 2x plus 3. So that would cancel. What do we have here? Let's see. Yeah, so we have 2x plus 3 minus 6. Or we have 2x minus 3. What can we do now? Factor out the 2. And here, you'll notice we found our x minus 3 over 2. That's what we were looking for. We need to write find a way to express that guy. So this guy here, I just found here. Now, remember what we want this to be. I'm saying this thing is less than my delta, which means that this expression must be less than 2 delta. And ultimately, I want this whole thing to be less than epsilon. So all I have to do is set epsilon equal to 2 delta. And so then my delta can be epsilon divided by 2. And so I'm going to go here and I'm going to fill that in. Epsilon divided by 2. And so now I can actually complete the process. I'm pretty much going to actually be recopying what I did over there. I just did the scratch work to make sure everything's working out nice and I don't need anything to worry about anything else. So at this point, I'm going to say, okay, so this I can do that. Cancel. That's equal to 2x minus 3. This is equal to 2 times x minus 3 over 2. and this is less than 2 delta, which is equal to epsilon. And so, I can even write it in if you want. Which is equal to 2 times epsilon over 2. The 2's are going to cancel. And so I get epsilon. And so what I have is that this expression, the f of x minus L, is less than epsilon, which is what I want. So any epsilon anyone gives me, I can get closer to 6 than that tolerance. All I require them to do is just to make sure your x value gets within that distance, half the tolerance that they told me. The x value has to get that close to 3 over 2. So, yeah, this was here with scratch work. So like on an exam or a test, or a test or a quiz or something like that, if I asked you to prove a limit, you would write down this sentence. And pretty much, it's a template that you're filling in. So you should be aware that what I'm underlining in blue, you pretty much always write that. Let epsilon be greater than 0 be given, choose delta equal. The blah you have to figure out. Then, if your x minus a is less than delta, we have your f of x minus a in f of x minus L is what you're going to put here in absolute values. Then you're going to do calculations to show that assuming delta is this, you would end up with something less than epsilon. And to make sure that that's going to work out nicely in your favor, go to the side and do a little structure. But the actual thing that is presented is going to be this script here. And that's how you prove a limit. Now there are classes who teach you how to prove. So in Calc 1, I'm actually not super concerned that people know how to prove things at the moment, but it is in our syllabus that you know how to prove this, so I'm going to pretty much tell you, follow the script and you'll be fine. If you just copy this down, as I said, and just fill in the parts that the calculation parts that you're responsible for, you get full credit for this problem. But making sure that what you're saying is actually making sense, that's something that at this stage it's not going to be, I think it'll take too much work to actually teach you how to know what you're saying makes sense. So just verbatim say what I said and fill in the calculation parts, and we're good. Any questions on any part of this? Yeah.
See how you factored in, you got x minus 3 over 2? Is that, and it was also the limit as x over just 3 over 2? Is that always going to be the case?
Where I factored what?
So see how you have the circle in red, like x minus 3 over 2, right?
Yes.
That's x minus c.
Yes, x minus the a. You always put, so this is
always
so this equal? Yeah. So when you're looking at limit of x minus a of f of x equals L, you're always going to fill in the a right here at this part of the script. You're always going to fill in the f of x right here at this part of the script, and the 6, which is on the other side, is the L. You always put in the L in this part.
And then,
yeah.
as you factored in, you got like x minus a in your line there, like in the word part. So you got the f minus L to eventually get to the x minus a. Is that always going to be the case?
You always set up f of x minus L. Ultimately, you do want to be able to see this at some point, because you want to replace that guy with delta. So yeah, you definitely want to start out with f of x minus L, but throughout your calculations, you should eventually see this guy pop up. That allows you to replace it with delta, which hopefully, if you choose your delta very well, it allows you to cancel everything and get epsilon. Yeah.
So I have a question about like the concept. So yesterday you were saying like all of this just shows us like us getting closer to like a specific limit. Like
Yes.
this is what you show me.
Yes.
Okay.
So epsilon is the units that someone tells you, I want to be this close. Right? I want to be 1 unit away. I want my y values to be within 1 unit distance from each other. So then you would respond to that person, okay, just make sure your x values are half a distance away from each other, and then your y values will be within 1 distance away from each other. And someone can ask another thing. No, I want them to be 0.01 distance away from each other. Then you tell them, okay, make sure your x values are 0.05 distance away from each other, and then your y values will be within 0.1, right? So I'm saying once your x value is this close to that number, the y value will be this close to that number. That's basically what you're saying. So, and that was kind of an attempt to really make the word close precise. How do you make something that's subjective precise? Let the person who's reading it choose what they want. And in this way, you just tell them, choose what you want. Give me any number greater than 0, I will make it work, right? And for this particular problem, any number you give me greater than 0, all you have to do is make sure that the x values get within half that distance, and it's going to work out. Now, pretty much at this level, C is going to be the most complicated kind of example you will actually see. Because that one, you're going to realize when you're over here, you're going to have like a little hiccup, and we are going to have to deal with that. Let's actually do the scratch word for that first. Just focus on that at a time, then we'll come back and do the script word. So let's focus on the scratch word. So I know ultimately what I'm going to want to be able to say. I want to say if the distance between x and 2 is less than delta, then the distance between x squared and 4 will be less than epsilon. That's ultimately what I want to show. Now I need to figure out the delta that's going to make that work. So what I want to do is to make sure I can somehow squeeze this x minus 2 out of this guy, replace it with delta, and then calculate what my delta needs to be. So how can we get that here? How are we going to get that x minus 2? Well, we get factor. So that's x minus 2, x plus 2. So this becomes x minus 2 times x plus 2, right? Now, remember I want that to be less than the epsilon, but so far now what I know is I want this to be less than delta. So this is going to be less than delta times x plus 2. And so I can set that equal to the epsilon because that will make it less than epsilon. Now, if I were to solve for the delta, I would end up getting this expression here. And it turns out that that expression is problematic. Do you see why it's problematic? Yes.
So we're for the denominator not being 0.
Denominator being 0, yes, that's one thing, as well as, that's one of the main things, as well as the fact that there's an x here is a problem, right? Because when someone gives you a tolerance, you can't actually respond with a tolerance of your own. Because the tolerance that you figured out has some variable in it, so you actually don't know what to tell them, right? You're going to tell them some number divided by, you're going to tell them the number that they gave you divided by some number that you don't actually know what it is, right? I mean, x plus 2 could be anything, depends on what the x value is, right? So that's not good enough because it has a variable in it. So you don't want any variables in it. You want someone to be able to tell you a number and you can tell them back a number. So that's a problem. So what we need to do here is to figure out, can I replace this x plus 2 with a number? Is there a way to actually say, okay, there's a specific number that I can tell you, divide epsilon by this number, and it's going to work out. And here's how you call this a trick. But the trick here, whenever you're in a situation like this, you try to solve for your delta to make everything work out, and somehow you have like variables in there that you don't really know what the delta is going to be. If not, they don't tell you the x values. What you can do here is put a max threshold on delta itself. So, for example, I can say delta, I want it to be less than or equal to 1 in all scenarios. Which means you just decide ahead of time. No matter what anyone says to me, I'm actually going to tell them the number 1 or something smaller is going to be what should be used, right? So once you set a max limit on your delta, in the beginning you might wonder how does that actually help us, but I can remember this expression here. If your x minus 2 is less than delta, and I know my delta itself is always going to be less than or equal to 1, this actually tells me that x minus 2 is bounded by 1. It has to be less than 1. Now if I have that expression, how can I rewrite that? How can you tell me about the x value? What does that tell me about x if I write this? Huh? Yeah?
Can't be greater than 3.
Sure, but tell me some calculations here, not no guessing. Yeah.
You would do x. It would be negative one plus 2 because you want to move that.
Well, don't skip any steps.
Is less than x minus 2, which is less than positive.
Right.
And then you would solve for that.
First, we could pre-calculate, right? Knowing how to deal with an absolute value inequality. Absolute value is less than a number. It opens up into a double inequality where you put the negative of that number on the other side. Now you can solve for x by adding 2 to everywhere. So I add 2 to this side, I would get 1. I add 2 to this side, I would get 3. So what I realize here is by me giving myself a limit that I will not pass, it forces a limit on the x itself. Now once I force a limit on the x itself, this is going to force a limit on the x plus 2. This is going to now be, if I can add 2 to both sides, I realize that x plus 2 is going to be less than 5. In other words, I can just make the assumption that in absolute value x plus 2 is going to be less than 5. So this x plus 2, which I didn't have any control over before, by me throwing in an additional requirement to make, this is making it even stricter requirement, I can somehow find a bound for that x plus 2. So I can replace that x plus 2 in absolute value with 5, and that will actually fix the problem. Now, in a situation like this, here's how you're going to write it down. So either your delta that you're going to choose is going to be the number 1, and that's going to work. In the event that that does not work, then I'm going to choose delta equals epsilon over 5, right? Because I know this denominator is bounded by 5. Yeah.
But by looking at x minus 2, how did we know that that was going to be less than or equal to 1? What tells us that?
Oh, well, this we know from the beginning, right? This is a part of the setup. But what we said, because we didn't really know how to deal with the x, which I do now need to know how to deal with the x, I can't have one inequality with 2 unknowns. That's too much. So what I do is I give myself a value, which is what I just did here.
So
I pretty much replaced the delta with 1.
We could have chose any number.
You can choose any number, yeah. Any positive number can work. 1 is typically what's chosen though, because it's just a nice number to work with. But in theory, I could say 17.9, right? And then I would say, okay, either you need to make sure your x values are within 17.9 units, Or if you realize that doesn't work, if you made it to 17.9 units and it's still not working, then choose this instead. So you give your person options. You're going to say either this is going to work or that's going to work. So this is what's happening here. Someone tells me I want to get within epsilon close for the y values. Then you say, well, make sure your x values are within 1 unit of each other. And if you realize that that doesn't work, make them within epsilon over 5 units of each other. Right? So now you give them options. They can actually choose one or the other. And one of them will work because we kind of forced it to work. When you have a scenario like this where your delta depends on the x's and you have to finagle the x's and kind of put an artificial bound on them, here's how the script is actually changed. So now you can see that delta is either going to be 1 or epsilon over 5 depending on the situation. How do you actually make this precise? How do you make sure that they can check it? Well, we're going to start the same way. Let epsilon here then 0 be given. You're going to choose, and here's how this part becomes different. You're going to choose your delta equals, and you're going to choose the best one at the time. You're going to choose the following. Choose your delta equals the minimum of 1 or epsilon over 5. Whichever value happens to be smaller, pick that one. So if someone tells me, oh, epsilon is 1, I want to be within 1 unit of the y values. Then you have to choose the minimum between 1 and 1/5. You would pick 1/5 to use. If someone says, oh, I'm fine with being 5 units, with being 10 units away for the y values. Then if you plug in epsilon equals 10, you get 2 over there. You would pick 1 for the delta instead, because the 1 would be the smaller one. You want the x value to get the closest as it can possibly be. So you make a choice between these two expressions. Right? So 1 is going to work, and in any case where that doesn't work, the epsilon over 5 is going to work. And just choose the smallest one from the beginning so you won't even have a hiccup. You won't even have to make a choice yourself. You make the choice for the person that asks you. Then, if x minus 2 is less than delta, we have x squared minus 4, which is going to be x minus 2 times x plus 2, which is going to be x plus 2 times x minus 2. That is less than x plus 2 times delta. But I know this is either less than 1 or less than epsilon over 5. So what I can do is that this is going to be less than. This guy has to be less than 5. We actually computed that. Your delta is going to be less than epsilon over 5, because we just did that. And these will cancel. We'll get epsilon. And in the event that 5 was even too big here, and this was something smaller than 1, which is what would happen if this would have been the value, we'd still get something less than epsilon over there, because we'd have epsilon times something that's smaller than 1. We'd still get something smaller than epsilon. So this actually deals with all situations. So whenever you have a situation where you're solving for the delta, and the delta itself depends on x's, which you don't really know, what you do is just give the delta an artificial bound. 1 is usually traditionally what is used. And then figure out what the x value is bounded by. And then you can just make your delta the minimum of your artificially chosen bound and the bounds for the x's, the x expression that you couldn't figure out before. And that will actually finish the problem. So like I said, that's the most complicated problem you can have for a problem like this, where you have to make a choice between two deltas. But in that case, that's how you deal with it. You force your x to be a specific value by forcing your delta to be a specific value. And I think that's all the examples I wanted to do. Your textbook should have a few more. What else do I want to do now? I do want to talk about something very, very important, but in the meantime, I think there's some definitions I want to reformulate for you. Just to wrap up the limits discussion. Now, limits are still going to be important, and I'm actually going to show you a different technique to solve limits in the future, but for now, we're going to wrap up the limit discussion with a few more definitions, and then we move on to something else. With the epsilon delta definition of the limit, so that's what is often called the precise definition of the limit. Sometimes people might refer to it as the epsilon delta definition. Once you see that mentioned, you know they want you to do kind of like what I was doing before, instead of the short calculation. We can redefine some terms. For example, I can look at continuity in a different way. We say f of x is continuous at x equals a if for all epsilon greater than 0 there exists a delta greater than 0 such that if your x values get close to a by that delta, then your f of x will get close to f of a, because we know for continuity the limit should be f of a. Your y value will get close to f of a within the given epsilon. So you can think of that as a definition for continuity, which you might have to apply. Now, in this class, I'm never going to ask you to prove continuity in this way, but just in case if you're ever in a scenario where they say, use the epsilon delta definition to prove that this is continuous, it means you need to prove this definition. You can also define in the same idea what it means for the limit to be something like infinity. You say, limit as x approaches a of f of x is infinity if, now epsilon is usually thought of as a very small number, so sometimes they write a different number for all big M greater than 0. There exists a delta greater than 0 such that if your x gets close to a by that delta, then your f of x will be larger than big M. Meaning no matter what number someone tells you, eventually your y values will be larger than that number by taking your x values closer and closer to a. So look at the example here. So let's say that's our graph, like something like a 1 over x squared. Someone can pick and you're looking at the limit as x approaches 0, 1 over x squared. What does that equal to? Well, someone can pick a number. Say they pick m is this, right? So they pick a tolerance. They give you an m. And what you can say is, okay, just make sure your x gets closer to 0 than this number over here, than this delta. And if they pick a bigger number, okay, what about if this is m? Okay, then make sure your x gets closer to 0 than that delta. What about this m? Well, okay, make sure your x gets closer to 0 than that delta, right? No matter what number they tell you, bigger than 0, it's not going to matter. Eventually, you can bring your x closer to delta, and your function is going to be above that m value. This is what it means to be an infinite limit. What does it mean to say the limit is negative infinity? Well, it means for all m less than 0, there exists some delta greater than 0, such that if our x gets close to that thing, our a value by delta, then our f of x will be actually smaller than the given m. And that's just to say, no matter what negative number you give me, eventually my y values will be smaller than that if I make the x values closer. I think that's all I want. Your book wraps up the section with that kind of these kind of definitions, so I thought I'd just mention them. So in terms of the epsilon delta stuff, you only need to know it as far as proving a limit that equals a number is concerned. You don't really, I'm not going to ask you to prove it using, to show that something is an infinite limit, and I'm not going to ask you to use it for continuity, but you do need to know how to use it to prove a limit equals some number. And as far as that goes, if you don't get the idea, follow the script and just know how to fill in the calculations. Know how to find the delta equals what function of epsilon. It should not have x's in it. If it has x's in it, you have to do like what I did with the last example. And then know how to show that your calculations lead to something that's less than epsilon. Other than that, just copy the script verbatim, and that's the proof. Very important proof. For those of you who are going to be math majors, you'll prove things like this again when you get to a class like, might be Math 308, or if not 323 in the very beginning. Limits are very important. Okay, and that ends this section. So now, believe it or not, you finally have enough to attack the rate problem. I remember, I think it was lecture 2, where I mentioned to you, okay, what is calculus about? Well, it's about solving two problems. One of them was the rate problem, the other one is the area problem. So now we're going to attack half of the reason why calculus was invented in the first place, to attack the rate problem. Well, actually, calculus as we know it was invented because Newton was trying to figure out an annoying physics problem, so he just invented a whole new branch of math to be able to solve that physics problem. If you want to get technical, that's kind of what happened. He was trying to measure the orbits of the planets in the solar system, and he's like, gotta figure out a way to know how fast this thing is moving when the angle from the sun is this. Invents calculus, solves the problem. Yeah, when you're a guy like Newton, you can do things like that. We're going to actually look at how he did it. So, we are going to attack the rate problem. So, there are many ways to state it, but I'm going to give you a very intuitive interpretation. Figure out how fast something is moving. This is called the rate of change of the object. That's it. And yeah, the problem is no more precise than that. It's a very vague thing. I want to somehow come up with a method that anything someone happens to look at, we can figure out how fast that thing is changing. Yeah, that's what we want to do. Now, when Newton was doing this, what he had in mind was figuring out how fast the planets were moving. But what he did was invent a general, didn't really invent it, I'm not being completely clear here. But what he did was invent a theory that can tell him how fast anything was moving. Then he applied that theory to the planets to solve his physics problem. So that's what we're going to do. We want to figure out in general, is there a general mathematical approach towards figuring out, if I'm watching something move, figuring out how fast it's moving, figuring out how fast it's changing. This is called the rate problem. How do we figure out the rate at which things are changing? Now in life, things change all the time, right? Tide comes in, tide goes out, sun rises, sun sets, plants grow and then they die. They're always moving, and you want to figure out how fast they're moving, because that way you can make plans, you can anticipate certain things happening, and that helps you to actually solve a lot of problems preemptively. And so that's called the rate problem. How do we figure out how fast something is moving? Let's consider an example. Now I'm going to make this very simplistic on purpose, because that's kind of how math works. Usually when you want to figure out something that seems very complicated and big and vague, you come up with a specific example, figure out how it works for that specific example, then you kind of extrapolate how it would work for a larger example. I mean, I think in high school geometry you saw some very nice, elegant examples of this. I remember when I was in geometry class and they showed me how did we figure out that the area of a circle was pi r squared. And yeah, basically they start with the area of a rectangle, they use that to figure out the area of a parallelogram, then they realized they used that to figure out the area of a triangle, and then they looked at the fact that, well, a circle, if you kind of slice it up like pizzas, each thing is kind of like a triangle, and then they arrange these triangles in a parallelogram, they use the same formula, and boop, pi r squared popped out. So we're kind of going to do the same thing. We're going to start with a very simple idea that we know everything that's going on in that idea. Then we're going to try to expand that idea to cover more complicated objects. So an object is moving at constant speed. So here's an object, we just pretend it's moving, right? Now I don't know how fast it's moving, I just know it's not changing. It's not speeding up, it's not slowing down, it's just moving steadily. Okay, so that's a very simplistic scenario. Things don't always move at the same rate all the time, but we're going to pretend that this thing is moving at the same rate all the time. Its speed is constant, it's moving steady, right? Let's say we can track it. It's a very fast-moving object. What I'm going to do is just suppose I'm measuring it over time. That's t. And I'm measuring the distance this thing has traveled. Let's make time in hours, just to be definite. Also to be very suggestive, I'm trying to be very suggestive here. Let's do distance in miles. So this thing is just moving at a constant rate. Okay, so I start a stopwatch at a certain point in time, at time equals 0. And I think of this object as being at position 0. Let the stopwatch run, forget about it, come back 3 hours later, and I realize that thing is now at position, let's say 150. Now it's moving at a constant rate, so this would be expected to be a straight line. It's not speeding up or slowing down. You have the same, every time you move a certain unit, the distance you travel is going to be the same all the time, because it's moving at the same speed all the time. So I realized that a straight line would be the best way to model this particular situation. And so now, here's a question. What is the slope of the line? What's the slope of that line? 50. interpret that 50? For this particular scenario, what does that number 50 mean? 50 what? 50 miles per hour. Now, notice here, you could set up, if you wanted, your two coordinates. Technically, slope, you know, is rise over run, so it's 150 over 3. But if you're calculating it specifically, what you would have is, you'd have the y2 minus y1, and that's measured in units of miles. Then you're going to have the x2 minus x1, that's measured in units of hours. So this isn't just 50, it's 50 miles over hour, or as you might recall, we shorthand that by 50 mph. 50 miles per hour. Now what is that? What is 50 miles per hour? That's the speed that the thing is moving at. Okay? So if I am measuring an object, and in 3 hours it traveled 150 miles, I can say how fast it was moving, 50 miles per hour. Right? It's not speeding up, it's not slowing down, it's just moving. If it's moving for 3 hours, it's going to cover 150 miles. So here's one important thing, and I chose these units to be very suggestive here, because we usually think of like miles per hour as the speed. That's what people know as the speed. More specifically, it's velocity, but we'll get to that later on. One thing you recognize from this is that our idea of speed is actually a ratio. If I take the ratio of miles per hour, people interpret that as speed. That's how fast something is changing, right? That's how fast this thing is moving. So there are two ideas we can take away from this. One, slope may be interpreted as a rate of change. At the very least, in this particular kind of example. And two, this is a ratio. So when you say, how fast is something moving? It makes it very vague. But if someone can ask, what is the ratio of these two numbers? Now it's very mathematically specific. Right? So we're starting to go from this vague situation to a more specific situation. Figuring out how fast something is moving is me figuring out a certain ratio. If I have a way to figure out that ratio, I can tell you how fast it's moving. One thing I also want you to take away from this, so I guess there are more than two takeaways from this, is that another one, as I confessed, I labeled these things to be suggestive, but we could have labeled these axes anything. And ultimately, the mathematical interpretation, how I would find the slope, would not have changed. So I could have been measuring something like, instead of distance versus time, I could be measuring, say, profit versus price. And I could think of that, again, if this were the case, I would actually be able to talk about how fast is the profit moving in relation to the price, right? So I can know, as price increases like this, profit is increasing like that. And to be able to say that this here will be 3 when that is 1, every time this car moves 1 unit, that moves 3 units, one way I can say that is, this thing is moving 3 times faster than that thing. So we'd be able to say, how fast the independent variable is changing in relation to dependent variable. When I take the slope of a straight line, I'm taking a ratio of the change in the dependent variable to the change in the independent variable, and I can measure that ratio as a slope. That ratio is called a slope, and that slope can be interpreted as how fast one thing is moving in relation to the other. So when I say something like 50 miles per hour, what I'm actually saying is, for this object, its change in distance is faster than the change in time by a factor of 50, right? So the distance is changing 50 times faster than the stopwatch is moving, right? So you also can think of speed as just a relationship between two things. I want to know how much faster than one thing is the other thing, right? So whenever two things are very important to me and how they're changing is very important to me in relation to each other, if somehow I can get a slope in the mix, I can talk about how fast one thing is moving in relation to the other. So that's the first kernel of the idea. That's the first part of actually solving the rate problem. And that was probably the most important idea. You take that idea and really flesh it out, really be able to apply it to anything, and follow it to its logical conclusion, and calculus. That's how it happens. So I'm going to show you how we're going to actually wrap this up and actually depend. How we actually wrap that up and actually put a mathematical meaning, a mathematical structure on these thoughts that we're having. Okay, so now the question is, what if we're tracking something that does not move in a straight line? Because, of course, not everything is going to move like a straight line, right? What if I'm tracking something like that, right? So here you can see it's moving, but then it started speeding up, then it started slowing down. What if something like that happens? What if the change is variable itself? It's not always changing at the same rate. How do I deal with that problem? Okay? So what if I'm measuring some function that's doing as it doing whatever it wants to do, and I'm concerned with, okay, at this point I want to know how fast is this guy on the vertical axis changing with relation to that guy on the horizontal axis? How do you solve that problem? And the answer, somewhat surprisingly, is to think like a flat earther, right? So, you know, flat earthers, those are the people who believe the earth is flat. And why do they believe the earth is flat? Well, they look around, it looks flat to me, right? Now, the earth is actually flat, is actually round, but why do they look at it as flat? Well, because they're so tiny that at their scale, something that's curving looks like it's flattening. That's our idea. The idea is, even if there's something curving like that, if you zoom in close enough, it's going to start to appear to flatten out, right? So there would appear that it's possible that I can draw a straight line through this point so that when I zoom in, the curve and the line are going to kind of start looking like the same thing, right? So you'd realize that if I can just look at this guy here and really enlarge the picture, really zoom in, then I'm going to have this straight line, like that. And at the same time, I'm going to have the curve touching the straight line. Now it's going to start being very close. It's still curving, but it's so close, it starts to look flat. And the more you zoom in, the flatter it looks. The more you zoom in, the more like that line it will look, right? So that's the idea. So if I have something, I know how to deal with a straight line. What if I have something that's not a straight line? The idea is zoom in until it starts looking like a straight line, right? Eventually, this won't happen for all curves, by the way. I'll talk about when you can't do this. But for a lot of curves, you can zoom in until eventually the thing starts looking flat. in the same way that the earth might look flat when you're looking around, but if you zoom out, oh, it's actually more spherical. But if I zoom in, it looks like flat land, right? So that's the same idea. We're going to actually take this idea. So I want to be able to zoom in so that that point that I care about looks like it's lying on a straight line. So the answer to the question I just asked was zoom in so it looks like a straight line. You probably don't have colors, but for me it's the pink line. Now, the pink line here, we give it a name. We call it a tangent line. Tangent means to touch, so it's a line that touches the curve at that one point. Which coincidentally, that's actually not a good way to look at a tangent line. I'll probably mention that again. A lot of people think a tangent line is something that touches a curve at only one point within a certain distance. That's actually not true. Tangent lines can actually touch the curve at multiple points. But whatever, the tangent means to touch, so someone came up with a clever name, tangent line. So a line that just touches the curve in that point that approximated the curve at that point, a tangent line. And the point of it is that this approximates the curve at the point of interest. So if I can draw a line through the point on the curve that I care about that approximates the curve at that point, meaning when I zoom in, the line and the curve look pretty much like the same thing, we say I've created a tangent line. Now, because I know how things work for a straight line, now the problem is almost solved. So we just then make the definition Matthew would just go around doing this all the time. Let's define this thing. We define the slope of the curve. What does that even mean? At that point, to be the slope of the tangent line. At that point. So now, because we know that we can interpret slope as speed, this seems to be able to solve the problem. If I want to know how a random curve is moving, how fast it's moving at a certain point, draw a tangent line there, figure out the slope of the tangent line, that's your answer. Easier said than done, at least at this point. We don't actually see how that's going to get done, but that's what we're doing. Figure out a tangent line, something that approximates the curve at a point, and then the slope of the tangent line, we'll consider that the slope of the curve. Once we can find the slope, we can tell you the speed of the curve. Problem? We only have one point. How do we find the line? Right? Now, if you have a straight line and you only have one point, how can you find the equation of the line? You need the slope, right? But the slope is what we're looking for. We don't know the slope. What's another way to find the equation of a straight line? What other information could you use if you don't know the slope? Yeah?
Can you use the derivative?
What is the derivative?
Doesn't that show you like the rate of change or something?
Yeah, but we don't know what that is. Right here I know what I have. I have a line that's going through one point. How do I find this equation? if I don't know the slope, because the slope is what I'm looking for. What's another way to find the line? Yeah. It's not a trick question, it's algebra question. If you want to find a line, you have to be given a minimum amount of information. You can be given a point and a slope. We don't have the slope. What other information can you be given? Yes.
Y2 minus Y1 over X2 minus X1.
Define what you're talking about.
Yeah, 2 points.
2 points. That's another way to find a line. If you don't have the slope and only 1 point, you need another point, right? You can find the equation of a line if you have 2 points. So far, we have 1 point, right? So that's an issue. We want to find the slope. I don't know the slope. What do you know? I know a point I want to pass through. Only one? Okay. So knowing 1 point is not enough. So here's what we're going to do. So here's the point I care about. This is the line I care about. And I want to find the equation of that line, but I don't know the slope. So the idea is just pick another point. Just pick another point. So that's what we're going to do. We go over here, we pick another point. This blue point. Some random point, right? Just pick another one. And at first you might wonder, well, how's that going to help us? Well, okay. With these 2 points, I can actually find a line. But that's not the line I want. Hold on a second. We can find a line, right? Okay, good. This new line is called secant line. Okay. So the tangent line is what I care about. I don't know how to find the tangent line. But if I pick some other random point, I know how to find the line that connects those 2 points. That point is called a secant line. That touches a curve in 2 points of interest. Now, here's the idea. The idea, what we're going to actually attempt to do, and at this moment, we don't actually know if we can do it. We are going to actually, point of interest, that's the other line. I actually care about the tangent line. So the idea is to do the following. Turn the secant line into a tangent line. Well, how do I do that? Well, you just pick a random point, so I assume you're not married to that point. What we can actually do is start making that point move closer and closer and closer and closer and closer to the original point that was picked. Now what you'll notice is happening once you're doing that is that the line when you're passing through these successive points, what do you notice about those lines? They're getting closer to the tangent line, right? So the idea is, okay, I picked 2 random points. I really care about this one though. So this one, what I can do is move him along the curve closer and closer and closer and closer to that one, right? The idea is, of course, to move the blue point so close to the white point, they're like right beside each other. So it becomes a scenario where drawing a line between those 2 points is kind of like drawing the line between 1 point. The 2 become 1, right? Essentially what you want to do is make the distance between the white point and the blue point 0. Now the white point is going to stay fixed because that's the point I care about. But the other point that I randomly just picked, let's change him to become what we want. Now, how you can start doing this, how are we going to start doing this? Let's start to get some math in here. here's our curve. Here's the point we care about. Suppose it is the point x. Let our curve be f of x. So this is going to be the point f of x. Okay? I'm going to pick another random point over here. And what I'm going to call that point, I'm going to call it x plus a little bit. Usually we use the variable h. H is going to be the distance between these 2 points. Now if that is x plus h, this point here is going to be f of x plus h. Right? So the secant line is the line going through those 2 points. Can I find the slope of the secant line? Of course I can. Using y2 minus y1 over x2 minus x1, as was suggested earlier. We can then find the slope of the secant. Well, it's going to be y2 minus y1 over x2 minus x1. And what is y2 here? F of x plus h minus y1 f of x over x2, which is x plus h, minus x1, which is x. The x of course cancel, and then with this expression here. What's that? That's the difference quotient. That's the guy that in algebra and pre-calc class they always ask you to compute it and they never told you why. Well, the reason why is because this is one step away from solving the rate problem. It's a very important ratio. F of x plus h minus f of x over h. Now, how do I turn that into a secant line? Or more specifically, if I wanted to find the slope of the tangent line, how would I do it? So now I know that that's the slope of the secant line. How does it help me to find the slope of the tangent line? Well, look at what we did. We wanted to move that point closer to this point. Now, what is that essentially doing? Is that you want to make the distance between these 2 points become 0, right? Now, the distance between the points is h. So in other words, what you are really doing to get this thing to work is to take this distance h here and move it closer and closer to 0. So we want an inch closer. Now these 2 points can never become 1 point because then I won't be able to find the line. But I want one so close to the other that it's effectively like they're 1 point. And so now I'm starting to think, do we have a mathematical mechanism to kind of inch closer and closer to something? I wonder what that would be. Any ideas? Yeah? Take the limit. What we can do now, so now we ended up in this situation. We're so close to solving the rate problem. How do we actually move this closer to that? Well, I don't know. What does it mean to get close to something? Go over here, invent the idea of limits, figure out how they work. All right, now we know what it means to get close to something. Then we're going to come back here. All right, I know how to get these things close. Take the limit of this thing as the distance between them goes to 0. And we have the slope of the tangent line. Now, this is a very important limit. It might not seem like much now, but it solves the rate problem. This guy represents, in one very small limit, how do we figure out how fast random things are moving? Now, throughout the course, I'm going to kind of explain to you how that actually works. But that's what this limit actually does. It's called, it solved the rate problem. So that's the idea. I figured out, okay, let's say, look at a simple situation. I have this object moving at constant speed. The graph is a straight line. Look at the slope of the straight line. Oh, that measures the speed that the thing was moving at. So now we're like, that's awesome, but what if it's not moving like a straight line? Well, if you zoom in, it starts to look like a straight line. Let's measure it by the straight line that it will start to look like. That's called a tangent line. Well, how do we find the tangent line? The slope of this thing. If I only know one point, well, take another random point and move that point closer to the first point. That's your slope. That is the speed at which f is changing in relation to x. Right? So difference quotient is important because it literally throw a limit on it and you actually solve the rate problem. Now, like I said, this guy is muy importante. Not Spanish, but you kind of have to say this in several languages. Anyone knows how to say that in French? I don't know. Very important. This limit is important. I think I already mentioned that. We give this limit a special name. We call it. Now, this is so important that math people sort of went outside of their comfort zone when it comes to naming things. I've mentioned this before, but math people really just name things by whatever they happen to be talking about at the time. So they're like, oh, this tells us that a continuous function will attain all intermediate values. What do we call it? Intermediate value theorem? Okay, this thing says that at this point, the rate of change is the mean value of the rate of change over the whole interval. What are we going to call it? Mean value theorem? Okay, this theorem is fundamental to the study of calculus. What are we going to call it? Fundamental theorem of calculus? When they got to this guy, though, they're like, no, we can't just call it slope. This is bigger than that. We call it the derivative. So then the math people were like, wow, this limit right here is really important. It helps us solve the rate problem. It allows us to find the slope of the tangent line. What are we going to call it? The derivative. Yeah! I totally brought this in. You have to commit to the joke. You have to. Okay. The derivative. That's what we call it. This limit is very important. We call it the derivative. And we have some notations for it. Notations for the derivative. Now, when Newton invented it, he invented something called the prime notation. Something that we're going to call this limit. So we have Newton's prime notation. And so basically, this is f prime of x. Because that thing here is called a prime. This is called a prime. It's like it's really elaborate apostrophe, but you might assume you write it as a notch on the board. So it's called the prime notation, and we call this f prime of x, right? And it means the derivative of f. In relation, remember, f is the output value, and our speed is meant to measure it in terms of the input value. So how do the f and the x relate to each other? The common phrase to say that in math terms is with respect to. So this is called the derivative of f with respect to x, or we simply call it f prime of x. And so that's called the prime notation. Now, a lot of people know this, but calculus was actually invented independently a couple of places in the world. Another guy named Leibniz figured out calculus a little bit after Newton. And they've always had a rivalry ever since. Newton accused this guy of stealing his work and all kind of stuff. Very, very dramatic stuff. But Leibniz came up with another notation called the Leibniz notation. And he called it, say, dy dx. Right? this is referred to as dy dx. Or you can think of it as, or where the y is the f of x. You could write df dx, that would be the same thing, but it's usually called dy dx. This is called the Leibniz notation. Now, one thing you notice about this notation, it's actually very versatile. I'll be stating a lot of rules in terms of this notation, but most of the time when I'm writing down a derivative, I'm going to use the prime notation. That's easier to write down, but this is actually, you can actually do calculations with this notation. So sometimes you can look at the d dx as its own thing and move the y to the side, so d dx of y. Oftentimes you can break apart the dy and the dx into separate entities and do calculations with them on a separate level. But basically what he did was, if you look at the change in y over the change in x, which is delta x and delta y, right? The triangle is the Greek letter capital delta. It's the uppercase version of this guy, right? And so it's just like he replaced the delta with a d to represent the fact that he's taking the limit as the delta x approaches 0. Right? So this is another way you can look at the difference quotient limit that gives you the derivative. But to represent that something special happened to the changing y or changing x, instead of the uppercase Greek letter d, he used the lowercase English letter d. So yeah, it's a very versatile kind of notation. And this leads us to the most important definition of today's class, and one of the most important definitions of the class as a whole. One of the most important definitions for the rest of your calculus classes, calculus 4, 5, and 6, you're going to need to know this definition in some capacity. Let f of x be a function. Its derivative with respect to x, so defining what a derivative is, if it exists. Now, it's a limit. We are aware that it's possible for limits to not exist. And the derivative, it's important, but it's also just a limit. So it has all the drawbacks that a limit has. So it is possible for a derivative to not exist. It's possible that the exercise that I just brought you guys through, you can't do it sometimes. And I'll tell you specifically what those times are. But assuming that we can do what I described, and this limit can be computed, it is given by the following. F prime of x equals the limit as h approaches 0. F of x plus h minus f of x over h. This is a very important equation. You need to know this equation. You need to have this memorized. But actually, what is the definition of the derivative? You need to write that down. Now this is also very important for you to be aware of. Interpretations. What is the interpretation of f prime of x? When you read that and you see this equation, yes, mathematically you can just, okay, it's that limit. But what does it mean? How do you apply this to situations? Well, one way to interpret it is as the slope of f at the point x. Another way to interpret it is the slope of the tangent line. To f at the point x. You can also think of it the rate of change of f. Sometimes this is called the instantaneous rate of change. I'll tell you about another kind of rate of change. But if someone just says the rate of change of f, or the instantaneous rate of change of f, they are referring to the derivative. How fast f is moving in relation to x. Think of it as the velocity of f if x is considered time. These are all very important interpretations of the derivative. So there are times when, to solve a problem, you might need to use a derivative. How do you know when you're in a problem where you need to use a derivative? Well, if you're looking for any of these things, you need to use a derivative, right? So these are the more important ones that will come up straight in applications. Interpretation of this it'll be very obvious when you have to use them. The question is pretty much going to say, you know, find slope dependent, find the equation dependent, do something like that. Once you know that, you are looking for the derivative. But these are interpretations. It is actually a way to figure out the rate problem. How fast is this moving? What is the rate of change of this thing? Well, if you can set up this limit, you can answer that question. And if you can't set up this limit at a certain point, it means it's not possible for you to know how fast it's moving at that point. It's just a little bit too crazy. So that's the definition. Have that memorized. Also memorize the interpretations. I should try to put this in a box too, I guess. Because it's very important that not only you know what it is and how to calculate it, but you actually know what it means, so that later on, when I'm giving you word problems to solve, you'll know when the derivative is necessary to use, at which point, if it's necessary at all. So that's going to be important. So it's called the derivative. So we've solved the rate problem. This guy is how we can figure out how fast something's changing. Let's do a straightforward geometric example so we can see how this will actually work out. Example. Let f of x equals x squared. A. Find f prime of x. B. Find the equation of the tangent line. To f of x at the point where x equals 3. So let's do this one. Now, x squared is a very nice example to use. Pretty much every book that talks about the derivative, looking at y equals x squared is usually the first example. Because it's complicated enough so it's not silly, but it's not so complicated that you won't be able to follow what's going on. It's a very nice middle ground. So let's actually do this one. So my f of x is x squared. A. How do I find f prime of x? How do you do that?
We bring down the 2 and then subtract the exponent by.
I don't know. What?
So it's like 2x, like the derivative of x squared is 2x because you bring down the exponent.
You don't know that. This is what the derivative is. So, in order to find the derivative f prime of x, we're going to use this limit. you know how to find the derivative this way. There will be problems that ask you to find the derivative this way. For sure, it's coming up on test 1, and pretty 99.9% sure it'll be on the final. You need to know how to find a derivative using the definition. Okay. So far, all we know about derivative is that equation. That's what it is. Okay, so how am I going to plug this in? What do I write? Yeah. Yeah.
X plus h squared minus x squared over 8.
Common mistake can happen here. Students often write x squared plus h separately. Don't be one of those people. I mean, f of x plus h means you look at the function, everywhere you see x, you replace it with x plus h. So we have this as the first step. So many students mess up on the first step, it's not even funny. Don't be one of them. Okay, now what?
That's going to be x squared plus 3h plus h squared minus x squared over h.
Yes.
And then you could cancel out the other.
A lot of students will write x squared plus h squared and forget to write the 2xh because they distribute the powers across the sum. Don't you haven't seen it. So, a lot of mistakes happen in the first two steps. It's so surprising. Even after me going through that speech in the first lecture, students still made that mistake for some reason.
The x is cancel out.
X squares cancel out.
And then,
Oh, I can cancel this h too, right?
no.
No, right, because you can't cancel across sums. You do any one of the mistakes that I just mentioned, you get a 0. I ignore everything else you write. So now what happens? Factor out the common h, because you can't cancel across the sum, you have to turn things into multiplication. H is now a common thing. If you factor it out, you have 2x plus h all over h. H is now canceled, and now you can take the limit. So remember, it's just the limit, so all your rules apply. Plug in if possible. Here we can't plug in because we divide by 0, so step 2 is try to simplify the plug in. And now we have simplified, so we can plug in. And so basically what we end up with now is the limit as h approaches 0 of 2x plus h. And I can just plug in h equals 0. 2x. So I can say here, if f of x equals x squared, then f prime of x equals 2x. I want to actually show you a very nice way to write this down, which I'm going to be writing down a lot of the derivative rules. One way this can be said in one nice short equation using the Leibniz notation is to say d dx of x squared is 2x, right? So the derivative of y with respect to x is 2x, where this guy here is the f of x, this is the y. So I can actually write that in one little equation using the Leibniz notation. So if f of x equals x squared, then f prime equals 2x, I can say that, boom, one equation, d dx of x squared equals 2x. And this is saying the derivative of x squared is 2x, right? So I can actually make this as a statement. And as we go through and we figure out some rules and we look at different functions, I'm going to be able to state rules to you like this. I'm going to say d dx of this function is blah. d dx of that function is blah. And you should know what I'm talking about. It means if you were to do this limit definition with that function, that's going to be the answer, right? So let's introduce a little notation there. Okay, so now we're going on to part B. How do we find the equation of timeline? What do we need to find the equation of timeline? Yeah.
Maybe you can do the derivative and then substitute the for x to get this.
Yeah. In general, what do we need to find the equation of a line?
No, in general, probably
y-intercept and the slope, or more generally, a point and the slope, right? We know how to find the slope. The derivative is the slope. That's an interpretation of the derivative. So this is just a straight line, which means we need a slope and a point. Now the slope, I know what that is. I can get that from the derivative, right? So I'm in a situation where I need a slope of this random thing that's not a straight line. What do? Derivative, that's what I want you to think. The derivative is interpreted as slope. Same thing. So if I want to find the slope of the tangent line, it's just the derivative. Where? At the point where x equals 3. And now, how do I find the point? Plug in. Well, the point is just x comma y, right? Where you plug in x and compute y. Right? So this problem, to answer this problem, breaks up into two sections. I need the slope and a point. I know I can find the slope from the derivative, and I know I can find the point by just plugging in the x value into the formula. So here I can say m is going to be the derivative evaluated at 3. Right? So f prime of x, which is this guy, gives me the slope for any current point x. If the x is 3, then the slope is going to be 2 times 3, which is 6. So at this point that I'm concerned about, the slope is 6. What is the point? Well, now I know that if x equals 3, this means that my f of x is going to be 3 squared, or it's going to be 9. So this gives me the point. So the point is 3, 9. So now I have that my slope is 6, and the coordinate I want to go through is 3, 9. Using a point and the slope, I can find the equation of the line using the point-slope form. So I'm going to have y minus y1 equals m, x minus x1. Y minus the y coordinate, which is 9, equals m, which is 6. X minus the x coordinate, which is 3. And that's actually your line. Now, you can occasionally write this as y equals mx plus b. In calculus, I don't tend to care usually, but you could if you wanted to. This is going to be equal to 6x. This would be minus 18 plus 9. So that's what, minus 9? Or you could write that. Now, what actually happened here? So just put a picture to this. What we were looking at was the graph y equals x squared. Now, for some reason, x equals 3, like x equals 3 was a point of interest. At that point, the y coordinate was 9. What we wanted to find was the equation of the line that touches this curve at the point x equals 3 in such a way that if I were to zoom in, that line would look like the curve. And what is that line? Well, this is going to be the line 6x minus 9. The y-intercept here is going to be minus 9, and the slope will be positive 6. And what I can actually say about this function is that at the point where x equals 3, x squared is moving at 6 units of speed. I'd be able to say something like that. At least 6 units of speed in relation to the x coordinate. So that's what we just found. We can draw a tangent line and we can find its equation. And once we know the slope of that equation, we actually know how fast something is moving along here. So if I put a point here and I say it's moving, you know, at 1 x unit per second, I know that it's moving at 6 y units per second at that point. So at this point, the y value is increasing 6 times as fast as the x value. That's another way to do it. Right? So there are a lot of interpretations here. But in terms of a straight up calculation, that was how you actually do it. Here's a function, find the equation of the tangent line. You need to find a slope and a point. You get the slope from derivative. Derivative is synonymous with slope. They mean the same thing. You just use derivative in a more general context, but it just means slope. More specifically, it means the slope of the tangent line. Right now, all we know about a derivative is it's that limit. So if I ask you to find a derivative at this point, you compute that limit. That's just how we do it. So you go through, you compute the limit. Make sure you don't make any of the mistakes, the algebra mistakes that I pointed out on the first lecture, in the first lecture. And yeah, at the end of the day, you should get through that very nicely. So that's the beginning. This is the beginning of differential calculus, as we would call it. We have a lot more to learn here, and we'll do that for like a really long time. The next 2 months or so we'll be spending on figuring out how to find derivatives in different contexts, figuring out shortcuts for derivatives, because using the limit definition can get annoying. As you will see, we're going to do a bunch of things with the limits, and yeah, we'll learn a lot of things about this, but that's the derivative, the solution to the rate problem. I will see you guys on Monday.